Hello students, now I'm going to explain about how this insertion sort algorithm works. So let's go through an example. Um, Before that, let me just introduce the basic principle of insertion sort. Given an array of size n with indices running from 0 to n minus 1, what we are trying to do is this. At any time, we are going to maintain two parts of the array. From index 0 to I minus 1, the array is going to be maintained as a sorted array, and from index I to n minus 1, the array will be unsorted. Okay, so this I is really the iteration index. So what we are going to do is at every iteration, we are going to pick up an element a of I, okay, which is the first element in the unsorted portion, and try to insert that in the sorted portion. Okay, so if you look at this thing also, this is the sorted portion, okay, from index 0 to I minus 1, and we pick this a of I and try to insert a of I in the right location in the sorted array. Okay, so wherever it gets inserted, everything to the left of it is less than or equal to this, and everything to the right of this is kind of greater than or greater than this a of I. Okay, so that's the principle. Now let's go to this example. We want to sort this array. Okay, so to start with, the first element is sorted by itself, so this is the sorted portion, and we want to kind of this is the unsorted portion from which we want to pick up an element and move it to the sorted portion. Okay, so we start with 23 actually, and we want to see where 23 can fit in. Okay, so what we're going to do is basically compare the element that we pick with every element in the sorted array. So there's only one element to compare with now, so we compare 45 with 23, and since 45 is greater than 23, definitely then for this is not the final position for 45 in the final sorted array. Again, in the final sorted array, this is not the correct position for 45, because there's at least one element, which is 23, we have found that to be less than 45. Okay, so 45 has to be at least moved to the right by one position, and that's what we are going to do here. So we are going to really copy 45, and this 23 is stored in this temporary variable v. So now what we do is we move to the left. So this is a comparison we just now did. We compare this 45 with 23, and since 45 is greater than 23, we really copy it here. And but 45 is still over here, but we don't have anything else to compare to the left, so it means this could be the final position for 23, but we're not sure. But at least for this sorted array comprising of 23 and 45, 23 is this is the final position for 23 for within this sorted subarray. Okay, so now what we do is, so this is the sorted array 23 and 45, and we have 8, 12, 19 and 21. So what we are going to do is we are going to pick up 8 and move and insert it to the right location in this sorted array. So we compare 45 with 8. Since 45 is greater than 8, this is not the final location for 45, so we copy 45 to the next position, and then compare 23 with 8. So again 23 is greater than 8, so this is not the final position for 23, so we copy 23. So when we copy 23, the 45 gets overwritten with 23, and there's nothing else to the left, so we insert 8 over here. So this is the sorted subarray, and this is now the unsorted array subarray. So now we pick up 12 and try to see where it could be inserted in the sorted subarray. Now 45 compared with 12, 45 is greater than 12, so we move 45 to one position to the right, and then compare 23 with 12, again 20 is greater than 12, so we move 23 to the right. So now we compare 8 with 12. Since 8 is less than 12, we don't need to move 8. So which means 12 cannot be to the left or in this position. Okay, so 8 is less than 12, so we insert 12 over here. Okay, And so this is now the sorted subarray. We now pick up 90 and try to see where it could be inserted. Now you see 45 compared with 90, 45 is less than 90, so 90 could not be either here or it cannot be anywhere on the left, so it has to stay wherever it was. Okay, so now we pick up 21 and see where it could be inserted. So we compare 90 with 21. 90 is greater than 21, so this is not the final position for 90. We copy 90 to the right, and then compare 45 is 21. Again 45 is greater than 21, so we copy 45 to the right. Then compare 23 to 21. 20 is greater than 21, so we copy 23 to the right. Then compare 12 is 21. Since 12 is less than 21, 21 cannot be either here or to the left, so it has to be here. So this is a final sorted array. Okay, now you see the kind of loop condition before that. So the iteration runs with I running from 1 to n minus 1, and every time we pick a of I to be v, and really we are really checking where a of I can fit in. So we start with I minus 1 and go back all the way to 0. So that's what this inner loop is really doing. This inner loop over here is really running from j equals I minus 1 and is decremented all the way until it reaches 0. Okay, and also we check a of j is greater than v, which means you see here when you compare when you want to insert 21, this is our these are our a of j's. As long as this is greater than 21, we keep moving to the left to see where this v could be inserted. So once we come across a situation where a of j is less than or equal to v, which means it is not greater than v and it is less than or equal to v, we come out of this while loop, because both the conditions have to be true for the while loop to execute. So once a of j is going to be less than or equal to v, so like in this situation where we come across a 12 which is less than really compared to 21, we stop the inner while loop and really we set what a of j plus 1 equals v. So that is this in this case j was really 1, right, because we compared a of j, which is 12, a of 1 is 21. So when we come out of the loop, j is 1 and j plus 1 is 2, so we really set a of j plus 1, which is a of 2, to be 21. So that is what we do here. Okay, so again when we see that a of j is less than or equal to v, like we see here, a of j is 1 is less than 21, we stop the inner while loop, we stop this inner while loop, which is this, and we come out and set a of j plus 1 to be v. So in this case j is 1, j plus 1 is 2, so a of 2 to be 21. Okay, and in the inner while loop what we really do is that copying business, which is like since a of j is greater than v, for example 90 is greater than v, so this cannot be the final position for 90, so we copy to the right. Okay, so that's what we do by setting a of j plus 1 to be a of j, and then we decrement and move to the left. So after we do all this copying from 90 to the j plus 1 position, we decrement j by 1, so j is really now pointing at 45, the index for 45. Okay, so that is how insertion sort works. So now let's do what is kind of the runtime the complexity analysis. Now with insertion sort, we will come across three situations for a best case, worst case, and average case. So the best case happens if the array is already sorted. So that happens, for example, if you have an array, say it is 3, 8, 9, 10, 12, and 13. So this is the sorted portion. We try to see where 8 could be inserted, but 3 is less than 8, which means this condition is violated, right? So 8 has to be here. and then we will check where 9 could be inserted, and since again 8 is less than 9, 9 has to be there. So by the way, this a of j greater than v, this is really our basic operation. This comparison that we do here is the basic operation. So how many comparisons we do when the array is already sorted? Okay, so we really have this already sorted, so we really run I equals 1 to n minus 1, right? So that is our outer loop, and for every I we really run this inner while loop only once. Actually the comparison is done only once, because once it is found that a of j is less than v, you come out of the while loop and set a of j plus 1 equal to v. So the complexity is I equals 1 to n minus 1 sigma, and we do this inner comparison only once for every value of I, so that is 1. So that is basically n minus 1 minus 1 plus 1, right? So that is n minus 1. So sigma, this is going to be n minus 1 minus 1 plus 1, so that's going to be n minus 1, right? So that is state of n. Now in terms of worst case complexity, if the array is reverse sorted, in the sense that we have an array where everything looks like this, say 13, 12, 10, 9, 8 and 3. So now this is the 13 is the initial sorted array, and we want to this is the unsorted array, and we want to see where 12 could be inserted. So 13 is greater than 12, so 13 has to be copied and 12 has to move in. So this would be what it is, 12 and 13. Okay, and now we have this unsorted portion. So now we pick up 10 and compare with 13. 13 is greater than 10, so what we need to do is we need to do kind of let me do 13 and 13, and then compare 12 with 10. 12 is greater than 10, so we really end up putting 12 over here, and since there's nothing else to the left, we really have something like this. Okay, so this is the sorted portion. Now we have the unsorted portion. So if we keep doing like this, again for 9 we really end up comparing it all to all the elements and then get the 9 inserted as the first element, right? So you see, then the number of comparisons we do is really what every time we run the inner while loop, right, we do comparisons where as you see here, for all values of j, and j runs really from what, I minus 1 to until it becomes 0, right? If it is, when you do j equals j minus 1, j becomes really negative, right? That's the time you come out, okay, because j is now 0 minus 1, negative 1, so negative 1 plus 1 is 0. So that's when the element a of I or v gets inserted as the first element. Okay, so the inner while loop is basically then executed at the worst case for all values of j. Okay, so that is j equals I minus 1 to 0, and then you have a 1 over here. So if you could rearrange this upper limit and lower limit, so this will be sigma I equals 1 to n minus 1, and this will be j equals 0 to I minus 1. Okay, so that would be if you rearrange this from I minus 1 to, so 0 to I minus 1, let me see if I can do it over here. So what you have is I equals 1 to n minus 1 and j equals I minus 1 to 0, and this is 1. So that's what we have. Okay, now as I said, this could be rewritten as the upper limit and lower limit could be rewritten like this, because the upper limit has to be always greater than the lower limit. Okay, so I could rewrite like this. So this is going to be then I can write this as I minus 1 minus 0 plus 1. So that is basically this negative 1 and this plus 1 cancels. So that is going to be I. Okay. So it's going to be I. And so that is nothing but what, 1 plus 2 plus 3 up to n minus 1, and that's going to be n times n minus 1 over 2. So that is theta of n square. Okay, so I think I can pull up the symbol theta of n square. Okay, so at the worst case, insertion sort is n square, whereas at the best case it is going to be n. Okay, so now let's look at what is its complexity at the average case. Okay, so on average, what we basically want to see is how many times this comparison is done. Okay, so the inner loop really runs from j equals I minus 1 to 0 or 0 to I minus 1. On average, we will really do, like when we look at the elements in the sorted array and do the comparison, on average we will do say half of the comparisons, right? Okay. At the best case we do only one comparison, at the worst case we really do all the comparisons. So in the average case, let's say we do half of those comparisons. So that's why you see the j index runs from j equals I minus 1 to I minus 1 over 2. So you start with I minus 1 and go all the way up to I minus 1 over 2. So again we could rearrange this to be this, the lower limit to be I minus 1 over 2, and this is I minus 1, and that really boils this down to like something like this. So let me rewrite it over here. So this is for worst case. And this is going to be for average case. And let's see, so this is running from I minus 1 over 2 to I minus 1. So that is equal to I minus 1 minus I minus 1 over 2, or if you want I can introduce something like this. So this is I minus 1 over 2 plus 1. So that's going to be I minus 1 minus I minus 1 over 2. So this portion is going to be I minus 1 over 2 plus 1. Okay. Now if you could do this kind of simplification, something like this, I could take an LCM and then I could make it like something like this is over 2. So this is I minus 1 plus 2. If I take an LCM, this 2 gets over here. So this is going to be I minus 1, I minus I plus 1 over 2. So I can really take this half out. So let's put up the equation again. And okay, so I can really make this half to be out. And this is now sigma I equals 1 to n minus 1, okay, I plus 1. Alright, so that is nothing but you still have this half. I'll write this half in parentheses like this, times apply the values of I. So when I is 1, is going to be 2 plus 3 plus 4 plus so on plus what, n minus 1 plus 1, so that's going to be n. Okay, so we really want to kind of solve this summation. So this is going to be, again, the half is still over here. Now if we want to apply our formula, this has to be 1 plus 2 plus 3 plus 4 plus up to n. So we added a 1 over here to bring in our formula, so we have to eventually subtract a 1. Okay, so we added a 1, so we have to subtract a 1. We transform this to basically this. So we added a 1, so we subtract a 1. Alright, so that's going to be again a half times. So this term is going to be really what? N times n plus 1 over 2. Okay. Introduce it if we want. Alright, so this is going to be something like n times n plus 1 minus 1. So the whole thing goes inside right. So basically you could stop over here and say this is what, theta of n square. Now you could do one more simplification, so I can write this as so LCM is going to be 2 for this, and there's a half over here, so it's going to be 4 times n plus 1 minus 2. So that now you can say this is theta of n square. Okay. Now let's pull up this problem. Okay. When do you say, so this is problem number 10 in this sample questions on chapter 4. Alright, so when do you say a sorting algorithm satisfies the stable property? Okay, so we want to also say whether insertion sort satisfies the stable property. Okay, so I could give the pseudocode for insertion sort, and we pretty much know by now how it works. Now, so when you say a sorting algorithm is satisfying stable property, which means if you have, say, two or more elements of equal value at indices say I less than j less than k. So they are appearing at these indices such that a of I equals a of j equals a of k. When we do all this sorting business, the original array ends up occurring with indices say I prime less than j prime less than k prime, such that a of I prime, wherever a of I was at index I, it is at I prime. Okay, wherever a of j was at index j, it is at j prime. Wherever a of k was at index k, is at k prime. But still, I prime is less than j prime less than k prime. Okay, so let me illustrate with this example. Let's say this is all 8s, so there are 4 8s, so it's sorted by itself, we know that. But let's subject this to our insertion sort. Okay, so 8 0 means it is at index 0, this is at index 1, this is at index 2, and this is at index 3. So to start with, we know that the first element is its own array, which is a sorted array, and the remaining elements are considered to be the part of the unsorted array. So now we pick up 8 1, which is our v, and a of I, which is 1, right? This is the first index, and really compare that with 8 0. And since we have a of j is I minus 1, j is I minus 1, so I is 1, so j is 0, so we compare 8 0. And 8 0 is greater than 8 1? No, because we are really comparing the numerical values here. So 8 is greater than 8? No, 8 is equal to 8. So this condition is false. So we really come out of the while loop and set a of j plus 1. J is going to be what? 0, because I was 1 and j is I minus 1, so 0. So j plus 1 is now 1 equals v, which is 8 1. So we really set 8 1 to be in the same location 8 1. So same thing happens for 8 2, 8 3, and so on. So what we really infer from this is the elements are not really moving around such that 8 1 appears before 8 0, or 8 3 appears before 8 1, and so on. So they are still holding on to their positions, their relative positions. Okay, so the array could have some other elements too, but still, as I say here, the indices are such that if a of I, if I is less than j and less than k of a of I equals a of j is equal to a of k, then the a of I moves to a of I prime, a of j moves to j prime, a of k moves to k prime, such that still this kind of relative ordering holds good. Okay, I prime is less than j prime less than k prime for a of I prime, a of j prime, and a of k prime. Okay, so which means insertion sort does satisfy the stable property. Not all algorithms will satisfy the stable property, but insertion sort does that, satisfies stable property. Okay, all right, thank you.